Okay. We want to introduce. Okay. Uh, Hello, everyone. Welcome to the crypto seminar. Today we have Rachit with us. He's going to talk about his work on time lock puzzles with efficient batch solving. This is his joint work with Jesco and Julio. Uh, yeah, Rachit, you can start.
Okay, nice. Hi everyone. It's good to see everyone there. And this is going to be an interactive talk, so please feel free to stop me or ask me any questions. And yeah, and is everything clear? Or okay, everything's good. Okay, so this is a work, time lock puzzles with efficient path solving, and it's with the co-authors Jesco and Julio, as Nikhil mentioned. And the hero of this talk is going to be something called as time lock puzzles. So let's begin with what are time lock puzzles. Time lock puzzles are a cryptographic object where a message M is locked for a certain amount of time, which means that it should take a lot of time to open this message. So it has two key features. One is called puzzle generation, which means that the time taken to generate this puzzle should be fast, ideally logarithmic in t. And generating this puzzle should be fast, but solving it should take a lot of time. And when I say it should take a lot of time, I mean that even if you had a very powerful supercomputer which can do a lot of parallel computation, you should not be able to do it much faster than time t, some wall clock time t. And the way it's going to be mathematically modeled is the circuit that takes this puzzle and opens it has to have a depth of size at least t. So this is the notion of a time lock puzzle. Puzzles should be easy to generate, but it should take a lot of time to solve them. And please feel free to stop me if anything is unclear. Okay. So what are the applications of such a primitive? You can encrypt to the future. You can always talk to people in the future if somebody is prepared to spend the computation time to open it up. But more concretely, you can do sealed bid auctions. Imagine if there are 10 parties who are all bidding for some art piece. All of them can submit their bids, and the bids stay locked for a certain amount of time. And the auctioneer then can open the bids in the required time. And the key thing is, like, once a bid has been submitted, the party who commits to the bid is like binding. And it's different from a commitment in that sense, because commitments you need to open. But a time lock puzzle, once you submitted it, anybody can open it. Just they have to spend the required amount of computation. So if you don't know anything about commitments, don't worry, but basically it helps in sealed bid auctions because you can commit for a certain, or you can encrypt your message and lock it for a certain amount of time, so nobody else can see it until that amount has passed. And once that amount of time has passed, the bidding phase would have ended, so nobody will actually know what you would have bid. And it's used in non-malleable commitments. So this is more of a theoretical construction where the structure of the time lock puzzle helps you build like cool applications for non-malleable commitments. And then it's also helpful in blockchain front-running prevention and some applications to Byzantine broadcasts, where basically the idea is that there are a bunch of adversaries who, when they're seeing the message, this message is time locked, so they can't really pick and choose to promote certain messages in the blockchain or to delay certain messages. And the idea is that after the time lock, by the time the puzzle should have been opened, the blockchain would have already been consolidated, and you have certain guarantees because of that. So that's the main sort of different flavors of applications of time lock puzzles. And it has many other applications, but these are the ones that I chose. And why is this relevant? I want to focus on applications where you have to solve each of these underlying puzzles. So imagine there is a setting, let's say it's an auction setting where 3 parties are bidding for a certain art piece. And party 1 bids message 1, party 2 bids message 2, party 3 bids message 3. And we want to solve each of these puzzles to know their individual bids. So we want to solve all of these puzzles, and this kind of application is useful in blockchains and Byzantine broadcast, and it really involves a lot of scaling. So imagine if you have to now solve all of these all of these time lock puzzles. The auctioneer has to solve all of them in parallel. And these are very heavy amounts of computation. So you can imagine when you're doing this sequential computation or this time t computation, it lasts a day. So it is a very heavy computation. And now if you have to do this for all three parties, that means either you have to do all three of them in parallel, but if you have like 1 million users, you have to do all 1 million of them in parallel. Or if you're doing sequentially, you would end up taking a long amount of time. So this is a big bottleneck when we are trying to scale these systems up. So we want to solve all of these puzzles, but what we are hoping is that maybe we can get it done more efficiently than just trivially solving each one of them in parallel. And another way we could see solving all of these puzzles could be an issue is if we're again in this auction setting, and if I as an auctioneer or I as a bidder just introduce false bids. So I'll just introduce for very, very short amount of bids. And because I've introduced these new bids, the person who's organizing the auction now has to solve all of them at once. And because they now have to solve all of these bids, there's hope of like, no computation ever being performed because it's like a denial of service attack where I've just flooded the system with so many requests that the person who's organizing the auction just does not know which ones are the true bids, and it just takes them too much computation power. So this is the problem setting that we're in. That there are multiple of these time lock puzzles, and we want to solve each of them. And solving each of them is something which I'm going to call batching in this talk. And what we really want is fast batch solving, which means that if you want to solve all of these puzzles at once, how much time does it take, or how much circuit complexity does it require? So the trivial solution in terms of circuit complexity would be n times t, because I have t sequential computation for one puzzle, and I'm measuring just the circuit complexity, which means now it's going to take, and if I'm solving all of them in parallel, it means it's going to take n times t. Is this sort of clear? Okay. What we really want, what I mean by fast batch solving, is I want something to be sublinear. So I want this quantity which depends on on t to be sublinear in n, and there is going to be another quantity which depends on n, because in the end you are solving n messages. So there is n communication that's being communicated. So you have to spend certain amount of time which is dependent on n, but the quantity that depends on n is logarithmic in t. So this is a non-trivial solution where the quantity that depends with t is sublinear in n, and the quantity that depends in n is logarithmic in t. Okay. Okay, so let me just continue what we do in this work. So in this work, what we show is that we can get away with solving exactly one time lock puzzle, which means this quantity here, the sublinear in n, it's a constant. It's just one puzzle, in fact. So the time that will take proportional to t, which is the most heaviest form of the heaviest computation in our system, is just going to be solving one puzzle. And by solving that one puzzle, we'll be able to open all of these remaining puzzles. Okay. So let me begin with our result. So we show how to construct such a notion where the goal is to batch solve these time lock puzzles. And the only prior solution before our work was based on indistinguishability obfuscation, which is not very practical at all. And there are some candidates even based on multilinear maps, but even those are not very practical. So that's a very heavy theoretical hammer, and we do not want to rely on that. So we instead give two concrete constructions and implementations, one based on learning with errors, and the other based on pairing assumptions. And I'll go through the list of assumptions that our work uses more clearly in the next few slides. And we also introduced this notion of rogue batch solving, where imagine now if you want to do this kind of a batch solving, where by looking at all of these puzzles at once, I'm able to solve all of them together. The circuit complexity just involves solving one time lock puzzle. What I do not want is, let's say if party 1 generates a puzzle and party 2 generates a puzzle, party 2, just by the process of generating their puzzle, is able to maliciously influence the way party 1's puzzle gets solved. So this will become clearer when I explain it more in the next few slides. But basically, what I do not want is malicious parties causing an error in correctness of batch solving. So a malicious party, just by changing their own puzzle, can somehow influence how everybody else's puzzle gets solved. Okay. Any questions? I feel like maybe I've rushed through this a little bit. If time lock puzzles is clear or batch solving is unclear, please let me know. Okay. Okay, I'll continue then. So in this work, the roadmap that we'll follow is we'll construct a batch time lock puzzle, which has this efficient batching property. And we'll construct this from an intermediate primitive, which I'll call coordinated batched time lock puzzle. This is going to be helpful for us to build the eventual thing. And I'm going to explain what this coordination notion is in the next slide. But this coordinated notion is an intermediate primitive, and we've built this from key homomorphic PRFs and linearly homomorphic time lock puzzles. So these are a mouthful of words, but I'll explain each of these primitives. So the goal would be to build this coordinated batch time lock puzzle. And then there is a generic transformation, which can turn any coordinated batch time lock puzzle to a general time lock puzzle. So we'll remove this relaxation on the primitive that we're going to assume. And the key ingredients is going to be a homomorphic PRF and linearly homomorphic time lock puzzle. So what is a linearly homomorphic time lock puzzle? So when I think of a time lock puzzle, there is like a lot of sequential computation involved to compute the quantity. But the other thing that we really want is we want the puzzle to be fast to generate. So one of these assumptions is this repeated squaring assumptions over the RSA modulus, where if I know the prime factorization of the RSA, I can compute 2 to the power t mod phi of n. So puzzle generation is very quicker. But if somebody is given to you x, has given x to you, it will take a lot of sequential computation, a lot of repeated squaring to reach to x to the 2 to the t. So every time to reach to the x to the 2 to the t, you have to square it, and then you have to square it again. So there is a lot of sequential computation, but there is a way to shortcut this computation if you know a trapdoor. So that's the pretty much the construction. This is the construction that Rivesh, Shamir, and Wagner had, and Malavolta and Tyagarajan in 2019 showed how to change certain aspects of it and make it similar to pi-layer encryption to construct something called a linearly homomorphic time lock puzzle. I'll also explain this in the next slide, but this is prior work. So I'm going to assume that we have this quantity linearly homomorphic time lock puzzle, and we have a key homomorphic PRF, and I'm going to show how to build this coordinated batch time lock puzzle. And then this key homomorphic PRF, we're going to have 2 constructions of it, one from learning with errors and one from pairings. And I'm also going to show you the pairing construction because I think I'll have time, and we'll move forward from that. Okay. So let's focus. Yeah.
So if I recall correctly, the learning with errors construction is only approximately key homomorphic. Is that enough?
Yeah, that's true. It's going to be almost key homomorphic. So I haven't mentioned it in the slide, but the homomorphism property is going to have some noise, and it's going to be almost key homomorphic. That's completely right.
Okay, so it's not a problem.
Yeah. So this is like a rough roadmap. We require one more, like we require a puncturable almost key homomorphic. I feel like I didn't want to like make too many words here, and I'll explain this when we go into it. Okay, so and then I'm going to show you the transformation from coordinated to batch, which takes any coordinated scheme and generally transforms it to a batched time lock puzzle. So just to begin with the notation, this time lock puzzle is going to have a setup, and setup is going to generate some public parameters. Puzzle generation is going to take these public parameters and output a puzzle. Puzzle solving takes this unary t operator, which means puzzle solving will take time t to solve, and it will output this message m, which is the underlying message which was locked or encrypted. And batch solving just takes n of these puzzles and solves all of them at once. As I said before, the key property of these time lock puzzles is that puzzle generation should be very efficient. So the puzzle generation should be logarithmic in t, both the setup and the generation. Solving can take time t, and batch solving, at least in our work, will take poly times t plus poly logarithmic in t times n. So the quantity that depends on n will be logarithmic in t. And I'm talking about the circuit complexity in all of these parameters. And we additionally have another setting in our work where we call something called as bounded batching, which basically means that I can a priori decide that my system is only going to batch 10 puzzles. And if I have such a notion, my setup algorithm is going to be augmented, and it's going to contain 1 to the power, it's going to take n as input, and the public parameters will grow with n. So it'll grow linearly or quadratically with n. It'll become clear when I show you the construction, but the public parameters can grow with n, and if they grow with n, that setting is a bounded batching setting. And the other relaxation I talked about is the coordinated time lock puzzle. What I mean by a coordinated time lock puzzle is basically that each party in the system has access to a unique index. So if there are 3 people who join the system, each one of them have a unique index, let's say index 5, index 10, and index 12. So this I is like unique to each party. And that's going to be my relaxation, and it's going to become clear why this relaxation makes it easier to construct the primitive. And once we have this relaxation where each party has this unique index, we will then get rid of it. So, okay, what's a linearly homomorphic time lock puzzle? If you're familiar with linearly homomorphic encryption, it is very similar, where if you have a time lock puzzle of message M1, if you have a time lock puzzle of message of M2, there exists an efficient transformation which does not involve solving each of these puzzles and then doing something, but it only depends logarithmic in t. And using this efficient operation, you can compute the sum of M1 plus M2. So this is still a puzzle which is locked, and it will still take time t to solve M1 plus M2. But if given those puzzles, it's easy to just create an encryption of M1 plus M2. Okay, and the other here I want to mention the fact that this is based on how the way I've set up the problem. This is actually enough to solve the problem we have. So if I want to now solve each of these time lock puzzles at once, one solution which I can do is if I have a time lock puzzle with message M1, a time lock puzzle which is locked with message M2, and a time lock puzzle which is locked with message M3, then I can take time logarithmic in t and compute this quantity M1 plus M2 times 2 to the lambda plus M3 times 2 to the 2 lambda. So I'm imagining each of these messages as a lambda bit block. And what I'm doing is I'm basically shifting it. So the first lambda bit block is the message M1, the next lambda bit block is the message M2, and the third lambda bit block is the message M3. And computing this is very efficient. And now I can just solve this one puzzle, which is this big puzzle, which has the summation of all 3 quantities. And once I solve this big puzzle, I would have recovered each of the underlying messages. So this is a valid batch solving solution. And here the complexity does not grow with n. The quantity that depends on t is the dependence on n with t is, so it's log n times t plus, log t times n plus t. So it's what we want. But there is an issue with it. Can anybody maybe try? What's an issue with this? What might be an issue with this scheme? Yeah.
Is there an upper bound on the size of the message that can be encoded in the time lock puzzle?
Yeah, that is one caveat, but even in our work, we present a construction which will also have this caveat. So that is a limitation, but that's not like the breaking limitation, or that's not the main issue with this. Maybe another attempt. Okay. So the other issue that will happen is that now when I'm encrypting a time lock puzzle, or I'm generating this puzzle, my puzzle size message space becomes huge. So now I have to support 3 times lambda bit message space, which means my puzzle size, which individual size which I give out, now it depends on the number of puzzles I'm trying to batch. This is not great, because now my communication complexity when I'm communicating these puzzles will grow with the number of parties. And it can become efficient if we have a lot of users in the system. So if you have like n parties in the system, and right now if I'm imagining all of these parties are talking to each other, this would lead to an n-cube communication, which is basically because each puzzle size is n, and now you have n square parties communicating, the total communication will become n-cube. So that's a lot of communication, especially in these scalable protocols. So there is another succinctness requirement which we ideally want in our scheme. Okay, sound good? Yeah, so here I've just graphically shown that the size of each puzzle will grow with n, which is the number of parties. Okay, now we are sort of almost ready to show our solution, but I want to introduce this primitive of a key homomorphic PRF because a few people might not know. And the primitive is a general PRF which has a key k, and PRF evaluation means it takes an input x and it outputs a value y. And the PRF security is like the general PRF security game, where either you are in this world where you're given a truly random function, or you're given a pseudo-random function, and you can make queries, and the goal of the adversary is to figure out which world it belongs in. So this is the general PRF notion. And by key homomorphism, I mean that if an evaluation of key k1 at point x, and there's an evaluation of key k2 at point x, then there is a way to compute the evaluation of k1 plus k2 at point x. So there is a homomorphism over the keys. And I'll mention it later, but there is this notion of almost key homomorphism, which will happen in constructions from LWE, which this relation holds with some slight errors. And that is enough to do our construction in the end. Okay. What we'll end up needing in our scheme is this notion of key homomorphic puncturable PRF. So what is a key homomorphic puncturable PRF? So it has all the properties that I discussed in the previous slide, and it also has PRF puncturing. So what is PRF puncturing? So you have a key k, and you have a point x star. And basically this operations allows you to compute this quantity such as punctured key. And the functionality of this punctured key is that you can compute on any point other than this punctured point. So once I've punctured it at point x star, you can compute the PRF evaluation at any point other than x star. So this is the correctness of this PRF puncturing algorithm. But what's the security? The security says that even if I'm given this punctured key and this point x star, so I know everything, I still will not be able to tell what's the evaluation at point x star. Any questions? So what's this puncturing notion? Okay. Now we are ready to do our full construction. So our construction is as follows. So recall that we're in this coordinated setting where each party has this access to this unique index I. So I'm going to call it party I. So the way party I is going to generate its puzzle is it's going to encrypt or time lock this key K. So I'm going to use encrypt synonymously, and throughout this talk, when I say encrypt, I mean time lock it. So I can encrypt this K, and then I'll output the message, which is a one-time pad of an evaluation at I. So right now I haven't done anything new because what I've done is basically a one-time pad. Like I've instead encrypted the key and used a hybrid encryption sort of technique to shift the message from the time lock puzzle to this key. Okay. The next ingredient would be in my construction, I'll give out this punctured key at this point I. So let's see why this helps. So this is our complete construction. Imagine if you want to compute the all three puzzles, like recover all the messages inside these puzzles. What I'm going to do, I have these values, these PRF evaluations, and I have like these punctured key. What I'm going to do is I have these underlying keys. So I'm just going to use my linearly homomorphic time lock puzzle. So K1 corresponds to the key in message M1, K2 corresponds to the key in message M2, and K3 corresponds to the key in message M3. And I'm going to use my linearly homomorphic time lock puzzle to now compute K1 plus K2 plus K3 encrypted under this time lock puzzle. Because I can solve at least one, I have like some amount of time to solve, I can open this time lock puzzle and I can recover K1 plus K2 plus K3. Because I have recovered K1 plus K2 plus K3, now what I can do, so let's say I want to recover message M1. If I want to recover message M1, I have this value, which is PRF evaluation of K1 at 1 plus value at message M1. And I can subtract the evaluation at K1 plus K2 plus K3 at 1. And because we have key homomorphism in this PRF evaluation, this basically means that what I'm left with is PRF evaluation of minus K2 minus K3 at 1 plus M1. So I have these other terms, evaluation of K2 at 1 and evaluation of K3 at 1, which I also want to get rid of in order to de-blind the message M and recover M. So to get rid of this, I'm just going to use the punctured key. So for this party, the punctured key is going to be K2 punctured at point 2. So because it's punctured at point 2, which is a different point than 1, I can compute the evaluation from the correctness of the punctured key at point 1. So I can then de-blind and remove the contribution from key K2 and contribution from key K3. And in the end of this computation, what I'm left with is message M1. If I have lost anyone, please let me know, because this is the entire construction. So okay. Does it make sense intuitively at a high level? We're using key homomorphism to over the puzzles to create a quantity which is correlated, this K1 plus K2 plus K3. And then we're using key homomorphism of this PRF evaluation to then sort of set up a cancellation solve. And then there are these other cross-term components that you need to cancel out, and that you're doing using because you've given out this punctured key. Okay, so let me convince you in one slide that the security of this scheme holds. The security basically should say that if the underlying time lock puzzle and the PRF is punctured secure, then this new scheme is also secure against any adversary depth which has less than depth T. So any circuit which any adversary whose depth complexity is less than T will not be able to recover the message M. And the way I do it is I first use TLP security to switch from K to random. And this I can do because my eventual adversary is also depth bounded. And once I've done this, I can then, there's no information about the key left other than the punctured key. And because the key is punctured and the evaluation at point I is still hidden, and I can change using punctured key security, I can change PRF evaluation of ki comma I from to random, and random plus mi is random. So that's it. So we have functionality and we have security, and this is our entire construction in a nutshell. Okay, so I've shown you how to construct a coordinated batch time block puzzle. And I wanted to briefly go over how to construct a key homomorphic PRF from pairings. So this is going to be an exact key homomorphism, unlike the LW construction, which is almost key homomorphic. But the key homomorphic PRF should have the following properties. There should be a setup algorithm, which has some public parameters or CRS, which is a structured string. And the key gen samples a key K, evaluation outputs a value Y, and there's key homomorphism and there's key puncturing. So puncturing basically means that if I have a point I can puncture it at point I. So the construction for pairings will have this relaxation where the input is going to be or the domain of the PRF is going to be bounded. So where here n is a polynomial, and basically the CRS will grow with n. So the puncturing construction is going to have this restriction where the CRS grows with n. So let me show you the construction. The construction is going to have these components, g to the x1, g to the x2 till g to the xn. And it's going to have these components egg to the z1 to egg to the zn. Keygen, I'm just going to sample a random element in ZP. And okay, maybe if someone doesn't know what a pairing is is an operation which allows you to compute, given g to the power x and g to the power y, it allows you to compute egg to the power xy. So my PRF evaluation would be egg zi to the k, and this has key homomorphism because if I do evaluation at k1, it has zi to the k1 and zi to the k2, and I can multiply them, and then it's zi of k1 plus k2. So zi is what I'm using for my PRF evaluation, and these xi component is what I'm going to use for puncturing. So the punctured key is going to be g to the xi to the k. And in the end, using the punctured key, I want everything to be evaluated. So if I puncture it at point I want to evaluate egg to the z times k. So to facilitate that, that functionality, I'll post these elements in the CRS as well, which is going to be these cross-term elements, which is zj by xi. So now if you have zj by xi and you have egg to the xi to the k, you can pair them up to get egg zj to the k. But notice that these cross-term elements, you are not giving out the self cross-term elements, which means whenever j is equal to I, you're not giving out that element. So the punctured key cannot compute at point I, but it can compute at point everywhere else. So that was the entire construction. Does anybody have any questions? Sorry. Okay. The key homomorphism part of or the punctured part of it is where we use the pairing. So I'm not going to sketch over the LWE construction, but basically in a prior work, it was shown how to use these BGG plus or style of like computation to get these almost key homomorphic PRFs. And that construction is a little bit more involved, but in our work, we realized that their construction was more general because they were building constrained PRFs. and we only needed to do this puncturing operation, so we could simplify certain components of their construction. And basically, we also have a construction from polynomial modulus LWE, which is nice because it works for a specific application. So, okay. Let me show you, if you've lost me till now, it's fine. Let me show you this transformation, which I get rid of this relaxation, where now each party has this index I, and I want to get rid of this relaxation. So this is a generic transformation. And how does this transformation work? So imagine I want to batch 3 puzzles, and there were 5 users in my system. So this is basically going to be a graph theoretical transformation. So what I'm going to have is I'm going to have these 4 slots, and now my each of my party is going to sample. So D is the degree of the graph. So each party, which is 3 at most, is going to sample 2 slots. So right now, I'm assuming that none of the parties have any coordination. So no, they do not know a priori which party might pick which slot. So when party A comes into the system, it sees these CRS, which consists of these 4 slots, and it just chooses slot 1 and slot 3. Party B, when it comes together, it chooses slot 3, slot 4, randomly out of these 4. Party C similarly chooses slot 2, 4. D chooses 1 and 2, and E chooses 3 and 4. How does this reduce to the earlier setting that we have? Imagine now if users B, D, and E want to come together to solve a time lock puzzle, or I as an auctioneer want to solve the time lock puzzles corresponding to users B, D, and E. I'll do is I'll look at this graph and I'll perform a perfect matching. And once a perfect matching exists, I have these unique indices attached to each party. So party B, what it did earlier is it had all of these time lock puzzles, but there is now a puzzle corresponding to slot number 3, and party D has a puzzle corresponding to slot 2, and party E has a puzzle corresponding to slot 4. So then now, because each of them have a unique index, I can then use my punctured key to do all of the things that I did before. And in our paper, we have an application of this theorem statement where we have very concrete parameters. And the analysis that we did is tight because we used Hall's matching theorem to perform our analysis. So that's an if and only if condition for an existence for perfect matching. And that gives us very tight parameters. Okay, any questions? Because this is a graph theoretical notion. So. Okay. Let me try to now discuss this notion of a rogue puzzle. So what is the setting of a rogue puzzle? So now you have these 3 puzzles and you want to open all of 3 of them at once. What's a bad condition? A bad condition is there's only one malicious party in the system, and I'm going to call party M1 malicious. And because party M1 is malicious, somehow they're influencing how party M2's message gets solved and party M3's message gets solved. So when I run this batch solving algorithm, which the auctioneer, let's say, does, maybe party 2's message gets evaluated to 100 and party 3 message gets evaluated to 1 million, which is like an arbitrary million quantity, arbitrary quantity. So that is something that party 1 was able to achieve just by changing its own message. So it's not changing the network or changing party 2's message. It's just changing its underlying structure to influence how other people's puzzles get evaluated. And let me convince you that that's a very real attack on the current scheme that I've given out. So in my current scheme, the only 3 things that I give out is a key K, a PRF evaluation of key K at point I plus MI, and this punctured key at point I. So how, does anybody have any guess, or how could I just changing my own puzzle cause the whole system to malfunction? So remember that in our batch solving algorithm, we were going to compute a homomorphism over these puzzles. So what I can do is I can basically lie on my what I have punctured and what I have encrypted in my puzzle. And if I lie, and if these two are not the same keys, when I homomorphically evaluate and I try to set up these cancellations, everybody else's cancellation is going to fail. So only my cancellation will go through if I set up my parameters correctly, but I can, just by changing party M1, by changing its own puzzle, can make sure that everybody else's evaluation does not work. Okay. The way we can fix this is by a validity check procedure, where in our final scheme, we have a non-interactive zero-knowledge proof, where which basically says that what I have committed inside the puzzle and what I've punctured in the key is the same object or same key. And once you have this guarantee from the NISIC non-interactive zero-knowledge proof, then you can show security against these rogue attackers. So basically, the idea is to show consistency between this puzzle and this punctured key. And additionally, there is issues if you the transformation might also have issues. For example, in the transformation, what was happening was like each party was sampling some random indices. And I can basically try to copy random indices of other party and cause like a perfect matching to not exist. And even this we can show by strengthening our parameters a little bit, we can get rid of it. So once these two conditions are hold, we can even show security against rogue puzzle attackers. Then we showed a prototype evaluation of our work, one in the batching setting. So this prototype evaluation, we performed a lot of sequential computations, and then we compared our solution with two other solutions. The one was the trivial solution where you're solving all of them in parallel. And the other one is the communication inefficient solution, where you have to solve, where you have to increase the size of your puzzle. And basically, if you were to do 50 million sequential computation, which basically means you have to do 50 million repeated squaring operations, and you were batching 500 puzzles, if I were to do trivial, then it would take 15 hours. And by 15 hours, I do not mean the wall clock time, because you can parallelize these 500 puzzles. What I mean is that what's the computation or CPU time that's being used here? And while our solution just takes close to 6 minutes. And to solve one puzzle, it would have taken close to 5 minutes. So this is quite close to our actual evaluation. And if we compare with the communication inefficient solution, our solution uses 37 megabytes, but the communication inefficient solution would have used 790 megabytes. The trivial solution would have been the best in terms of communication, because we don't have to do these. We don't have to sample a lot of these. Like in this case, we had to sample 4 copies of it because of our transformation from a coordinated to an uncoordinated world. And additionally, you have these punctured keys, so that takes some space, and even the PRF evaluation takes some space. Okay, so in conclusion, we gave a template which said that given any key homomorphic PRF scheme and a time lock puzzle, I can a linearly homomorphic time lock puzzle, I can do batch solving. We introduced this notion of a rogue puzzle attack, which basically means if I can just change my own puzzle to influence how everybody else's puzzle gets solved, those attacks should not be possible in the scheme. And we gave some concrete implementation and numbers. That is it from my end. please let me know if you have any questions.
I have some questions. Can
Okay.
go back to the construction of the file. This page.
Mhm.
Here you need to add key one and key two and key three together in the puzzle, right? But
Yes.
although the PRF is homomorphic, but if the process of computing the secret key of key one plus key two plus key three is not linear. So
So there is going to be some coordination between. So there is a linear homomorphism over the same space, if that's what you're trying to ask. So this PRF key, in the case of what I showed in the construction, is over ZP. But if it was this linearly homomorphic time-lock puzzles, it would be over the space of Zn. But because n is bigger than p, they are, you can imagine both of them are computation over Zn.
Okay, so here the homomorphic of the PRF, you require that to get a key of to get the secret key. For example, if you add key one and key two together, you can homomorphic evaluate instead of you do some other process related to key one and key two, right?
I'm sorry, I did not follow the question. What are you trying to, like, at least what's the goal of the question? Is it, are you trying to understand the protocol or?
Go to the page of construction of the key homomorphic PRF.
Yeah. So this construction?
Yes. Okay, so here the key homomorphism to get two key for example, to get key one plus key two, you need a times key one plus times key one and key two, right? Instead of add them together.
The operation is multiplication, but after the operation, the result is that the keys are added together. So
and also how to do the multiplication in the time-lock puzzle. I mean,
So-
the time-lock puzzle is linear homomorphic, right? So
okay, so I understand your question. So the time lock puzzle I'm only using to compute K1 plus K2 plus K3. Once I've computed K1 plus K2 plus K3, I forget all about the time lock puzzle. So there's no other operation on the time lock puzzle I'm computing. And then this evaluation, this is the PRF evaluation. So this has certain homomorphic properties. So after the only goal of the time lock puzzle is for me to compute this quantity K1 plus K2 plus K3. And then once I have K1 plus K2 plus K3 in the clear, so this is like in the clear, I can compute the PRF evaluation at 1. And if these keys are now related to each other, I can then remove and recover. Does that make more sense?
can I take another look at the construction of key homomorphic PRF?
Yes, please.
Okay, I understand. Okay, thank you.
Any other questions?
Yeah, is there an easy way to turn the, to puncture the LWE construction? I'm just curious.
So the LW construction is, there are already constructions of key homomorphism. It's a construction of Brzezinski and Vaikunthanathan. And basically, you have like S times A, where S is like some LWE secret, A and like these errors. And you can compute operations on them, homomorphic operations. So it's like S times A plus X or times the gadget matrix. I'm not sure how much I should go into like LWE specifics, but in the end, what happens is after you have these constrained PRF constructions, where after a certain operation, you get f of x times this gadget matrix, and as long as like this f of x computation of this function is equal to 0, then all these things cancel out and you can recover it. So as long as you have this constrained quality, you can recover k times x, or the PRF evaluation. And all of these are like almost key homomorphic. So there is some like rounding that you do towards the end.
Right, can you repeat how you do the puncturing?
So the puncturing is a technique which was popularized by BGG plus. It's
Typically for the LWE one,
yeah, so
you know a nice way to do it, or that's not known at the moment.
there is no nice way other than doing the BGG plus way.
Okay,
Which-
fair enough.
Yeah. Any other questions? So their construction actually has a universal circuit on top of things to do, but we changed it to an equality check circuit, and there are some like low-level details, which I don't have a slide for it because I thought it might be too domain specific. And a lot of it is like, I would say, careful engineering based on what we needed, but not all, any of it isn't surprising because it's just the functionality what we needed at the end. So there weren't any tricks or any cool observations I had to show there. There is one cool observation because usually puncturable PRFs do not exist from polynomial modulus LWE. LWE is an assumption. The modulus size grows, and you want a modulus size which is small because that means better parameters. If the modulus size is too big, then you have to represent group elements and everything is bigger. So you would ideally want polynomial modulus. And in our construction, polynomial modulus works because we can have the keygen algorithm depend on the punctured point. And this relaxation is enough to do our eventual combining of everything. But it's not enough to just build a generic homomorphic PRF.
Yeah, it seems like a very clean construction of batch puzzles.
I have one question.
Yeah.
Over here is n the number of parties.
So n in this key homomorphic PRF is the domain. It depends. If you look at this transformation, it won't be the number of parties. It will be like 2 times in my theorem statement I have it here. If it's 2 times e times n, where n is how many users at most I want to batch together. So to answer your question more concretely, n is how many users at most I want to batch, which is the number of parties. And the slots, or my PRF parameter could be 2 times e times n, or it could be slightly more.
Understood.
Yeah. In practice, like all of these public parameters are very, very efficient. So the way we did our numbers, our goal was to minimize the degree. So what we did was we chose like some candidate parameter, let's say 10 to the power 5. Even if you have to batch 7,000 puzzle, we set the number of slots as that, minimize the degree, and did a binary search to minimize the degree. And once we minimized the degree, then we figured out what's the minimum slot parameter we could pick. And then so we did this like sort of like circular way of like figuring out the right parameters. But all of these theorem statements are very tight. So we believe like they are the right choices.
Any other questions? If not, then we can thank the speaker.
Okay, thank you.